Thank you.
Yeah, that's crazy, isn't it, Kelly? I don't know. It's just nuts. Is what it is, I guess. I mean, it's fine as long as everybody doesn't start looting and everything. It's just crazy, breaking stuff. So the test is, come on, give it to me. Oh, here's the review. I'll hide this guy's ugly mug. Let's go big. There we go. Cool. So this is very similar to what you should expect in the test. I don't try to get too fancy when I make up these tests. Sometimes I do a little bit, I don't know, a little different here or there, but it's the same basic number of problems, the same kind of things I think are kind of fun. So you hit the bullseye when you're playing darts approximately 40% of the time. What's the probability the first time you hit one is on the 6th try? Okay, first of all, let's start with this first sentence. Right here, if that's all you saw, think about this. What kind of distributions could this be? Okay. What could this be before you ask any questions? What could happen here? Anyone?
You either hit it or you don't. So binomial.
Yes, it could very well be binomial. Yep, that's crystal clear. And then I could ask you something like I did here, where it's the first time you hit it is on the 6th try. Then that makes it geometric. Well done, Tim. Well done. And let's probably get at least. What's the probability you will try at least 4 times before you get a bullseye? That is also geometric. Yes. So yeah. So at least 4 times before you get a bullseye. So at least. What's the difference between these two? This is a PDF. It's a PDF on this one here because it is on exactly the 6th try. When you say at least 4 times, we're talking about that's greater than or equal to. So that's one I would like to just kind of work out and talk through a little bit, that particular one. So I'll switch computers here real quick and we'll bust through it a little. Somewhere. Oops, no, it's already up, stupid. Nope, I'll open it. Excuse me. What the devil? All right, so our P here is 0.4, I think we said. That's what we said, 40% of the time we hit it. Okay, and then we said something to the effect of, what's the probability you will have at least 4 tries before you get one? Okay, well, it could be 5 tries or 6 tries or 7 tries or 8 tries or 9 tries or so on. So clearly it's a geometric situation, but it's going to be, we need to look at it with a PDF standpoint. So I'm going to rewrite this as probably x is greater than or equal to 4. This is not a CDF, not a CDF, because a CDF is always less than or equal to some value. Okay, and most people use big X is less than or equal to little x. Okay, that's CDF. Okay, we don't have that. But what we always do in this situation is we always look at what's the opposite of greater than or equal to 4. Well, it's less than 4. And we know that this sum has to equal 100%. And that's cool. However, we're not done yet. This is also not a CDF, and that's because it's not equals to. Well, that's nice because there's nothing between 3 and 4. You're either 3 or you're 4. There's no in-betweens. So we can rewrite this as this. Nice. And so if I wanted to solve for this, I'm just going to end up subtracting this to the other side. And so the probability that x is greater than or equal to 4 is equal to 1 minus the probability of x is less than or equal to 3. And somewhere I'll get my Excel up. So remember, Excel doesn't have a strictly geometric distribution. So oh, fart, where'd you go? And so what we'll use instead is what it truly is. It's like a rectangle or a square is a rectangle. A rectangle is not a square. So what we do is it's a negative binomial distribution. Remember, negative binomial says you're going to play until you win this many times or whatever. That's nice. But a specific version of this guy is the specific version of the negative binomials when you play until you win one time. Okay, and that makes it a geometric distribution. Okay, so here we go. So number of failures. Okay, so we want to have 3 or less failures. Okay, before we hit one. Okay, so now if you go back and read the question, I think it was you have to throw at least 4 times before you hit one. Okay, so if I threw 4 times, well, that means that I had 3 failures and then 1 hit. Okay, so in this situation, you got to think about that. It's 3 throws. That means we're gonna have 2 failures. Oop, what the heck was that? I don't know. Touchscreen sucks sometimes. 2, 1 success. 0.4 is my probability of success, and 1 right there makes this. That is the geometric CDF. And we're just going to do 1 minus that guy. Okay. So there's a 21.6% chance.
Weren't we saying that the failures were 3 because you have at least 4?
No, I think it said you had to throw at least 4 times. But you keep in mind, at least 4 is this guy right here, right? This is 4 throws, and we want to include that guy. You with me?
Yes.
So we want to keep that. So we're going to get rid of everything else. We're going to subtract from below that.
Okay, thank you.
Mm-hmm. So the final answer comes out to be about 21.6%. All right. Does that make sense? Yeah, probably. So think about it. What's the probability you make it on the first try? 0.4. Okay, so I can make it on the first try, or I can make it on the second try, which would be 0.6 times 0.4. That's cool. Or I could make it on the third try. And remember, that's all this thing is you're multiplying your P's and Q's. There's no other way for it to happen. You had, in this case, because it's a geometric, it had to be fail, fail, fail until you win. Okay, and if you pull the, I'll pull up a quick calculator here real quick. That's 4% or 40% rather. So look at 0.4 plus 0.24 plus 0.24 times 0.6, I guess. Yeah, so that's 78.4%. And so that means the other 21.6% is above that, okay, which is what we just found. But again, the CDF is a beautiful thing to use. The tricky part is making sure that you get yourself a CDF. This is a CDF, okay? So if you're going to play that game, it's great. You should. I totally am for it. But make sure you're dealing with an actual CDF. Rookie mistake is to look at this guy and go, oh, that's a CDF because it's equal to. It has to be less than or equal to. Okay? That's just how they're set up, and that's just how they've always been done. So because by definition, that's just how they work. Okay? Questions on him? All right.
Can you go back to that formula real quick, please? Damn.
This formula? Yeah.
And the Excel spreadsheet.
Yes. As I share myself again.
Can you click on the formula again?
Yep.
1 because success, 0.
Well, no, 0.4. 0.4.
Oh, 0.4. Thank you. I'm a little blind today.
Here, let me fix that.
I will. Oh, shit. Click on it one more time. I'm just going to screenshot it.
Yep.
Thank you.
Nope. All righty then. So where am I? I forget which computer I'm on. It's too much. Share screen. There we go. Cool. So on this guy here, when you look at that, just because there's a zillion things going on, REEITMET, it right off the bat sounds like it's going to be probably multinomial, yes? And that might or might not be true. The difference is that if it were percentages, I would 100% agree with you. If there were thousands of each of them, I would 100% agree with you. It's multinomial. The fact that there aren't that many of them right off the bat suggests to me this looks like a very small candy dish. And when I take 2 or 3, or in this case 7 out of it, I'm going to be drastically changing the probabilities. Okay, so I'm going to go ahead and copy this down. I'm going to go ahead and write this on another. Well, maybe I am. What in the hell? Oh no. View option here. I don't want to stop this sharing. No, I don't care. Here, I'll just pull it up here. I just got to talk to myself while I'm doing this here. I write it down. Sorry. There we go. No, it's wrong. What the heck? Oh, it's on the computer. That's right. Oh, here we go. Let me write this down, and then I'll share with you when I get it down. So in the room, there are 10 REEs, 5 IT, 3 MET, 14 EEs, 7 MEs, 7 chosen, probability 3 RE, 1 T, 1 MET, 2 EEs. Gotcha. Okay, here we go. Let's share this. All right. Am I sharing with you? Can you see that?
Yes.
Yes, we see it.
Oh, that's funny. I don't see it on my other computer. What's going on here? Oh, I'm just on the Zoom. That's what happened. Okay, there we go. Perfect. Nice. So again, because there's so few of them, it's very similar to just a little candy dish. So obviously it's going to be changing things. So this is what we call hypergeometric, remember? Hypergeometric. And so in this situation, what's going to be in the denominator? How many people total are there? I think there are 39, 15, 18, 32, 39, 39, and we are choosing 7 of them. And then on top, we have the 10 REEs, and we're choosing 3, and we have 5 ITs, we're choosing 1, and 3 METs, choosing 1, and 14 choose 2, and 7 choose 0. I include everybody because I think that helps. Remember that if you add up the numbers on the left on top, they better add up to 39. The numbers on the right on top better add up to 7. I just think it helps sell the bit in my mind. It makes me feel like I'm doing a better job. Didn't forget anybody. 7 choose 1, 0 is 1. 14 choose 3 is, don't tell me, 242. Let's see. No, it's not either, you dumbass. It's 121. 14 times 3 divided by 2 is 7 times. No, it's not right. Ding dong. We'll just do the math, Jay. 14 times 3. 14 divided by 2 is 7. 7 times 13 is 91. There you go. I think that's right. We better check. I feel just wrong now. And I don't know, 10 choose 3. It's been a while. Let's see here. So let's just do it on Betsy here. 10 math probability. Oh, not random. Math 320. And let's do the other one real quick again. 14 math 91. Nice. All over 39. Oh, fart. 1538. 1538. 0937. So on top, 120 times 5 times 3 times 91 times, oh, times 1, stupid. Whatever is that. And then divided by 15380937 is about 0.07. 0.007. Or about a 0.7% chance of that happening. Okay. Remember, the fact that there are this many possible outcomes says that none of them will be really, really likely to happen because you only have 100% to go around. So when you go out, when the little probability fairy goes and distributes the probabilities around, nobody can really get that many because there's so many of them, okay? That's just how it goes. This isn't very likely. In this case here, you just said we're not getting any of those guys. That seems a little odd. Getting 3 REEs seems a little odd, and when you're getting 2 double E's, yeah, it's a little weird. So yeah, this is what this is saying to me. It's a little strange, and 0.007 is a tiny little probability there. Okay. Again, when you first looked at that, you know, your first thoughts might have been several things, but the key takeaway is there aren't many of them there. You expect to show all of our work, show the work that I kind of set up there, you know, so I can see where you're going, where you're getting the numbers from, not some random answer. I hate when I'm grading a paper and I don't know what you did, and so I can't, in good conscience, I don't want to take a ton of points off, but by the same token, I gotta feel like I need to be able to see what you're doing. So about what I'm showing is perfect. You didn't need to write down, you know, the 120 or whatever, like 10 choose 3 times 13 choose whatever. And you look at the formula in Excel to send that. I can, but I prefer that you'd write it down, just kind of write on paper like 10 choose 3 times and then do it in Excel too or whatever. So it's just that it's easier for grading purposes. I can kind of fly through it and see where you're at. If I get some random answer and then I have to go searching through the thing, and maybe it's easy on yours, but somebody was not easy to find. It just speeds the process up a little bit. And if I get the wrong answer, but you showed the right amount of work, and I go look at the Excel, and then, oh, well, yeah, you just typed something in stupid. That's easier. And I feel like I do it better. It's a more fair version of the grading when I do it that way, in my mind, anyways. Okay. Let's see what we got over here. Oh, that's the problem. This thing is full screen. All right. So in here, there. And scroll, let's go big. All right, oh, fart. Okay, so this one here, start with that as a PDF from 1 to negative infinity, from 1, well, that's just really weird. It should be from negative infinity to 1, I guess. Maybe it should just be 1 to infinity. Well, let's find out. How would I know whether it's supposed to be positive or negative infinity? Because first of all, I look stupid, right? The way I just wrote it here, obviously. That I should have caught that mistake before. Clean as the nose on your face now. So clearly can't go to z. Can't be going from negative infinity to 1, obviously, because you have to go over 0, and obviously 0 would cause us no end of trouble right here. This piece would be tending to 0, and then infinity minus 1 is basically infinity. E to the negative infinity is going to 0 on the top end. So yeah, this makes perfect sense. It should have been a positive infinity there. Okay. So what's the expected value and what is the variance? So I am going to try this and see if I can do this right this time. No, oh, no, stop. I almost cut off the meeting. That would have been funny. That would not have been funny. Here we go. So let's just first of all say, is it a PDF? Again, on 1 to infinity. 0.2, oh, you already pulled the 0.2 out, ding dong. 3e to the negative x minus 1 plus 2 over x squared dx. All right, let's just confirm that that sums to 1 on the interval there. Calculator's not helpful. There we go, that's more better. So escape, home. All right, so F3 for calculus. And don't forget your 0.2, dummy. 0.2, and then 3e to the negative x minus 1 plus 2 divided by x squared, comma x, comma 1, comma infinity. And I'll go ahead and show the infinity here, and we'll see that it works. If it doesn't work, I'll show you a different way around it. Oh, look, it worked. Yay, it sums to 1. So to find the expected value, I'm simply going to then just throw right here an x in front of that guy. So that's what I'm going to do is just go back and edit this, come right back in here and go x times parentheses. Bam. Oh, fart. What? Oh, never mind. I'll see if the parentheses in the right place, you ding dong. Okay, so there has to be a parentheses here to integrate with. Hopefully. Oh, for God's sakes. I suck at life. Okay, I got an extra. There's my problem. I got an extra one right here, I guess. Is that what I want? See what the pretty print looks like. X times the whole shebang. That's a problem. This is a bit of an issue. What's going on? X times that whole thing. That's fascinating, isn't it? Okay, that should have worked. Yes, okay. X times. That should still work. Oh, fiddle faddle. I don't believe it. Let's get in here. Let's get rid of this guy here. We'll just do it with an indefinite integral. There you have that. E to the x. Is there a giant negative somewhere? Where'd my negatives go? Uh-oh. Oh, there's my negative x out front. Okay, there it is. So, Yep, it is going to be a problem because of ln of x right there. Interesting. Interesting. Okay, well, I'm going to change this problem up a little bit. So it's my job. It's my game. I can do it if I want to. All right, so let's just make this e to the negative x. How about that? And let's go back and double check that we have. I'm just going to go back and double check that I have a PDF now. I'm going to add in the appropriate whatever it takes to get this to work. There we go. Oh, maybe if you actually integrate it from somewhere to somewhere, you ding dong. All right. And what is that as approximate? Come on, give it to me. Just what you wanted to see on a Wednesday night. Watch someone fool with their calculator. 3.1-ish. So we're going to do 1 over 3.1. So something like that. So about 0.322. 0.3222. Wow, lovely. Great. So I'm just going to confirm that that works real quick. Grab this guy. Stick out front of it. 0.3222. Good enough for what I'm doing. It's 1. Okay, it's good enough. I will make sure the ones on the test work perfectly. Okay, piece of cake. Now, so I'm going to come in here and I'm going to add in an x times right here. And I'm going to close the parentheses right after that guy. So my expected value, what did, oh, I didn't, oh, I guess I didn't hit parentheses. There you go. So my oh, you son of a buck. Ah, I'm going to hurt somebody. What is going on? All right. This is not this hard, Jay. Okay, let's say we have this problem. E to the negative 2x. All right. And we're going to go from 0, you see, to infinity. All right. Nice. Now, let's see if we can find if this isn't actually a PDF. Good Lord almighty. This is a ridiculous day. All right. E to the negative 2x. Beautiful. Comma x, comma 0, comma infinity. Dun, da, 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 and the answer is 1/2. Lovely. Check it out. 2. Beautiful. So this is a PDF. Yes. So if I want the expected value, it is literally the integral from 0 to infinity of x times my PDF. dx. Same thing as always been, and it's pretty straightforward. You come in here, give it the old, in this case, since it's a monomial, it just is e to the negative 2x. I don't need to do this, but I usually just do this, get in the habit of it. Make sure you include all of that in the parentheses. And then hit enter. And lo and behold, the expected value is 1/4. See, it's not that hard. You do it right, Jay. Cool. What is the variance? Well, remember the variance is the expected value of x squared minus the expected value of x squared. So to find this guy, it is simply the integral of x squared times your PDF from 0, in this case, to infinity. And the thing I love about the 89 is you literally just come in here, give it the old square, hit enter, and voila, maybe. I said voila. Come on. Come on now. Well, I'm just going to overclock you. What do you think about that? Bam. Now there you go. 0.25, yada, 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 yada. Okay. So it's basically 0.25. Good. Great. Lovely. So if you do this, it's going to be 0.25-ish minus a quarter squared. And so, that's the thing. Make sure you un-overclock it. So it's going to be minus 0.25 squared. And there's your variance, 0.1875. Boy, took a long time to pop that out. Okay. Now, what's the probability that x is greater than 4? Okay, you're like, ooh, I could use a CDF for this. You totally could. You totally could. First of all, let's just do that real quick. What would the CDF be? The CDF would be the integral from your lower bound, 0, up to x of your PDF dt, I like to use, okay? And then when you're done, this will be a function of x, okay? So in this case, it'd be from 0 to x of e of 2, e to the negative 2t dt. And so my CDF would be, boom, and you need to go from 0 to x. So that thing right there is your CDF. I'm going to write that down. 1/2 minus e to the negative 2x over 2. Okay, remember this is your CDF. It is the probability that x is less than or equal to some value of x. Okay? So the case we were asked about was 4. Now remember, it's a continuous distribution. So the probability that x is less than or equal to 4 is, remember, the same as probability that x is less than 4. Make x is less than 4 because the probability that x is equal to 4 is 0. Okay? So what we're going to do here is we're just going to stick into this guy. If we stick x equals 4 into this guy, if we say it's 1/2 minus e to the negative 8 over 2, this is equal to the probability that x is, I'm just going to call it less than or equal to 4, but it makes no difference because, again, 4 is equal to 0. So, so grab that guy. I like to go such that x equals 4. But you can just dump it in if you want. Notice that's 0.4998. 0.4998. Well, that's not what I wanted. I want the probability that x was greater than 4. So that plus this is equal to 1. So just subtract this to the other side. So the probability that x is greater than 4 is equal to about 50%, give or take. Okay. Those are the kind of problems that I will do on that. I will do that a bunch on that problem. I want that to be pretty straightforward for you. So I'll start off with a situation where I say, listen, here, here's a PDF, or verify that it's a PDF, something along those lines. Then I'll have you find expected value and variance. And I for sure will have you find probably the x is either less than 4, between here and here, whatever it is. I may very well ask you for what is the CDF, okay? Those are the kind of questions that I'll ask in the continuous distribution portion of things, okay? That's what I want to see is in that regard. Any questions on him at all? For 5 and 6 on the review, I'm going to, I'll do them, I'll probably make up a separate video for that aspect of it. 2 reasons, because that was the latest video stuff. Some of you may not have seen that yet. Also, it's one of those ones I like to do off to the side and not have to sit here and have you watch me maybe mess it up on camera. I hate that. It's very annoying to me because it wastes your time. So I'll make sure that those are smooth, but I will make a video explaining those 2 in a little more depth. So when you see them and you're like, oh, okay, that's what he's doing here. It's not just the answers, whatever it is. Okay. Moment generating function. I do want to mention this, and it was mentioned in that video. So the expected value of x is what we refer to as the first moment. Expected value of x squared, of course, is the second moment, and so forth. And so in the old days, and it's still kind of true, but it's not as true as it used to be. In the old days, it was really, it's always true. It's harder to integrate than it is to take a derivative, okay? And so the point of doing the moment generating function is that you create a function such that when you take derivatives of it, the first derivative will give you the first moment. The second derivative, evaluated properly, will give you the second moment, and so on and so on and so on. So in reality, instead of doing a bunch of different integrals, you have to integrate once to get the expected value of x, to integrate again to get the second moment, and so on and so on. Instead of doing a bunch of integrals, you do one integral, which is a fairly easy integral to do. Kind of. It will almost always converge. You'll be using L'Hopital on it. Again, if you haven't seen the video yet, watch the video on it. But when you get it, then it's simply a matter of taking a derivative. Any fool can take a derivative. That's what makes it really nice. And by the way, the derivatives will always have an e to the negative t in them. And so it'll always be a fairly easy derivative to take. Fairly easy. You'll almost always have chain rules. So if you're in the old days, you're like, oh, well, taking derivatives is not that hard. Yeah, oh yeah, then dumb chain rule comes along. So, but it was still easier. And so it's still a thing. It's not a hard thing to do. And if you've taken differential equations, when you do, come on, Jay, transforms, Laplace transforms, it will look exactly like what you're doing here. Okay, so if you've done a Laplace transform, it is almost identically what we're doing here. We're doing something completely different with it, but the process is very similar. Okay, and so I just want you to kind of think about that. In reality, it becomes, if you will, the expected value of e to the negative st is what you're finding. And so it is exactly what you think it would be, e to the negative st, well, t, I should say st. Anyway, so it's just whatever. So you'll see it when you go through the whole process. I'll just say that for later in the video and I'll walk through it. And as far as x and y being independent, on number 6 there, remember if they're independent, then their joint distribution is just the product of them, right? And so their joint distribution would be e to the negative x minus y. And then we'll talk about how we find the distribution of z, which is y over x. It's a transformation problem. If I do that to you on the test, well, if I put one on the test, I will put one on the test, but I will tell you exactly what to use. In this case, you have y over x is equal to z. We're gonna have to introduce another variable, and I'll show you how that works, and I'll spell it all out for you. That's great. But on the test, I will make sure that it's very clear for you. I will not leave it that way, because this class being out, it's fully online basically now. We didn't get enough time to work with those, and that's kind of how it is. Normally in class, I spend a lot of time doing that for a day, and even then people are a little tenuous with it. So I'll be gentle, I promise. Yeah, number 7. I will show it my hand here, but I would totally do that one. Actually, I'm not going to do that. I'm going to do it all in Excel. That's just way too hard. So I will bring up my Excel here on this other computer, and then share it with you. Stop sharing. Oh, wait. Oh, damn it. I was sharing. Rats. Here's my Excel, and if it's me, zero, 2, 3. Oh shoot. 0, 2, 3, 5, 8, 12, 0.6, 0.1, 0.08, 0.06, 0.09. Okay, and that should take care of that. In that situation, the expected value then, we had a question there. Saw someone had a question. What happened to it? Oh, fiddle. Where did the comments go? There. Chat. Who's chatting? Yeah. That's what I'm gonna do. Yep. All right. So what just happened here? Okay. So for the expected value of X looks like this. This is one where I totally don't care if you just use Excel for it. That's pretty straightforward. That's what Excel's made for. Expected value. Well, I shouldn't have said that. That's X times F of X. It's going to be my F of X. It's going to be my expected value column. I should have done it that way. I'm sorry. It's going to be X squared times F of X. There we go. And so equals this dude squared times F of X. Bam. So equals sum of these guys. That is your expected value of X. And then the sum of these guys, just drag that over. So this is the expected value of X. And this is the expected value of X squared. Cool. So then the variance would be variance is equal to this dude minus this dude squared. There you go. And of course, if someone asked you, hey, what's the standard deviation? It would be the square root of this dude. So 3.63 or thereabouts. Okay. Yeah, that's all I have to say about that one, I guess. Nice. Oh, fun. Hey, so on the test on number 8, if you're not seeing this, I'll pop it up for you. Love this question or questions like this, because this is stuff that you will run into in your walk with statistics. So you have 3 parts, a bushing, a gear, and another bushing that will be assembled side by side. And the bushings of normal distribution of 1/4 of an inch thickness, standard deviation of 0.04, gear has a mean thickness of that, standard deviation of that. What is the mean thickness of the whole assembly? Okay, so the mean thickness of the whole assembly would be 0.25 plus 0.25 plus 4.3, which would be 4.8. That would be the average or the expected value of the thickness of the 3 of them together. Remember, when you're adding, you always add the averages. But the variation's the standard deviation's a little different, excuse me. So remember, standard deviations, whenever you do an addition problem or a subtraction problem, you always add the variances, okay? And so you put sharing, and you start sharing, you this. Okay, so our variances were 0.04, or that's our standard deviation. So 0.04 squared. Oops, that is an N. I don't know what that's about. 0.04 squared plus 0.04 squared, because there's 2 of those guys, plus 0.2
You're not sharing anything.
Oh, dadgummit. Thank you. Share screen. You're not missing much. I just use my calculator here. Okay. And that is the variance of all three of them. Standard deviation of all three of them would be the square root of that mess. So when it wants to know what is the standard deviation of the length or the width of all three of them sandwiched together, that's what you would get. Remember, adding or subtracting, you always add the variances, all right? Again, the way I always think about it is when you look at couples' ages, the difference in couples' ages or the sum of couples' ages, you could get some freakishly weird, far apart in ages, so you get radically, hugely different, an old man and a young girl or vice versa. And you could end up with, if you take the man's age minus the woman's age, so if the man's 80 and the girl's in her late 20s, so Hugh Hefner style, that's a huge like 60 or 70-year difference. And yet if you had like a 70-year-old woman and a 30-year-old dude, that's a negative 40. And so you went from numbers that weren't that big to huge spans, from way positive to way negative. The variance is always going to get bigger, whether you're subtracting or adding. If you're adding their ages, you get a couple of 90-year-olds, and all of a sudden you got 180 up on the top end, and you get a couple of 20-year-olds, you get a 40 on when you add their ages. And again, that's a huge difference. So whether you're adding or subtracting, always add the variances, not the standard deviations, the variances of them. Okay, and then because they're all normal, then my new assembly would be, it would have a mean thickness of 4.8, we said, and a standard deviation of, what did I say, 0.207, 0.208 or something, 0.208. Okay, and that's all there is to that. Pretty straightforward problem there. It wouldn't be that big a deal. Remember also that we have two bushings. So I could have added the bushings like so. I could have said, well, it's 0.25 and 0.25, and I could have just added them, which is what I did, equals this plus this, and you got 0.5, obviously. But remember, it's the expected value of 2x, but that's equal to 2 times the expected value of x. And so the expected value of two of them is the same as 2 times the expected value of one of them. Well, 2 times 0.25 is 0.5. Okay. What is the variance of 2x? Yeesh, I don't know, Jay. What is it? Well, it turns out it's equal to, oh, I shouldn't have written it there, is equal to 4 times the variance of x. Okay. And why is that? Well, if you recall, the variance of 2x is equal to the expected value of 2x squared minus the expected value of 2x squared. This thing inside is the same as saying 2 times the expected value of x squared. So this is 4 expected values of x squared. And then this here, okay, well, this is the same as saying the expected value of 4x squared, which is the same thing as saying 4 times the expected value of x squared. So they both have a 4. We pull that out, and lo and behold, you get this. And what is this? This is the expected value, or this is the variance. This right here is the variance of x. So it's 4 times the variance of x. Okay. So what does that mean? Well, remember on our bushings, they had a standard deviation of 0.04. So 0.04 squared, right, times 4. We get that thing right there. That is the variance of 2 of them. But I could have done it this way too. I could have just said, well, listen, it's 0.04. What am I doing? Hold on. 0.04 0.04 plus, for God's sake, don't turn off over there. So when I'm adding these two guys together, all right, I add their variances. So it's 0.04 squared plus 0.04 squared. What am I doing wrong? Something's goofy here. Yes, what is going on? Oh, something's screwy. Something's going wrong. Come on, Jay. You can do math, buddy. So it's the variance of one of them is 0.04 squared times 4, right? Add their variances. Okay, I'm screwing something up. Yes, but what am I doing wrong? Something's a little screwy there. I'm not holding my mouth just quite right. So, okay, this is pretty straightforward. It's this way here. I would say on this last problem, what I would have done, I would have just done 0.04 squared plus 0.04 squared plus 0.2 squared, like I did on the calculator. You could have done. I'm doing something. I'm not holding my mouth right with two washers. Something's just not quite kosher there. It'll come to me in a second. The math's right. I was typing something in kind of goofy. So that kind of annoys me. But there will be a problem like that. Like these bushing deals, I think that's a big deal to me, to see how those pieces fit together. That's something I think if you take not a whole lot else away from this class is knowing that when you put stuff together, and knowing that they're going to have different things happening because of that, that's a big deal to me for you walk away from my class. Nice. And I shouldn't have shared that. I'm going to write that down first before I share it. And I'll just share it on the other computer here instead. So on this one, I guarantee there will be a joint like this. It's pretty straightforward. F of x and y. Okay, x squared plus y squared. 0 elsewhere. 30 to 50. 30 to 50. Cool. All right, so I need to find k, and we need to find the probability that x is less than 40, y is greater than 35. Nice. And we want the marginal of y, marginal of y. All right, so let's share with you. Okay, there it is. So to do this problem, of course, we are going to integrate. Why are you here? K x squared plus y squared, 30 to 50, 30 to 50, dx dy, or dy dx, it doesn't matter in this case because they are the same. And so, what just happened? Oh, stop it. Double integral x squared plus y squared. Oh, that's a plus, stupid, not a times. It matters. Did you know that? It's kind of weird, huh? It's kind of strange. Oh, that's more better. Okay, it's better. It's still kind of gross. Let me get a decimal for you, friends. There you go. Yeah, gross. Okay, that's what it's equal to. So of course, to the -1. There you go. 7.6 e minus 7. That's what I'm going to write. So k is equal to 7.6 e minus 7. Excellent. So I'll probably make it a little nicer on the test, but whatever. So 7.6 e minus 7. And remember, it should integrate to 1 now. So if I want the probability that x is less than 40, I better integrate from my lowest bound up to 40. And I want to go from 35 up to my upper bound. Okay. So I will just do this because I'm kind of lazy. I'm going to take that guy times, go grab these again, and then I'm just going to edit my limits of integration. Oops. 30 to 40, ding dong. There you go. And 35%. Okay. Now, how do I find the marginal of y? Marginal of y means that I better end up with a function of y, which means I better get rid of all my x's, which means I'm going to integrate, I'm going to take my function and I'm going to integrate the x's out of it. So I'm going to integrate across the entire spectrum of the x's, dx, and when I'm done, I'm going to have a function of y, and that's all I'm going to have left. Let's get rid of this, 30 to 50. Get rid of that extra integral in there. Yeah, there it is, okay? Oops, shoot. There it is. And I'm not going to write that down. You can just look at it for a second, I guess. Notice that if I change this up and I went and I integrated it with respect to y instead, I would get a marginal of x, which should be awfully similar. And it is. The question is, when you multiply them, remember the marginal of x, if the marginal of x times the marginal of y is equal to the joint distribution. What do you know about x, the function? What do you know about x and y? They are what to one another? If this is true, then what? X and y are independent. Okay, they're independent. Okay, so those two disgusting functions that I got, there's no way that they're going to multiply out to that decimal that we had times x squared plus y squared. It's not going to happen. What does that tell me? It tells me that in this case, x and y are not independent. Okay. Probably will ask you a question like that on the test. It wouldn't shock me at all if I asked you something like that on the test. Okay. Something else I could riff on this problem with would be something like this. What's the probability that y is bigger than 20 given x is equal to 3? Okay. Well, now that's interesting. How am I going to deal with this problem? Well, remember, it is the function of x and y divided by the function of x only, the marginal of x only, such that, I'll write over here actually, such that x is equal to 3, and then integrate with respect to y. Okay, that's what this problem is asking me to do. There should be no x's in this problem when we get done. Okay, because when we get done here, so we get f of x and y on top. Everywhere there's an x, you're going to throw a 3 in there. Here's the marginal of x, great, throw 3 in there. There's not going to be any x's left over. Everything's going to be y's and constants. Then I'm going to integrate from, well, did I say y greater than 20? That's 100%, friends, since they're all bigger than 20. Here, let's try this. So we integrate from 35 to 50, let's say, and there you go. So remember, that's not a very hard deal. It's just some of those things you have to do. You have to find your marginal, and there it is. By the way, this is the reason that this is true is because what would happen if they were independent? This guy on top would be the marginal of x times the marginal of y. And when you divide it out by the marginal of x, you are left with the marginal of y. In other words, it doesn't matter what x is doing because they canceled out anyways. That's the whole point of why it works that way. Okay. So could see a question or two like that on the test. So let's, I guess we'll go ahead and pop one of those out like this one here, but we'll just do this one here. So 35 to 50. Now I know what the marginal of x is. It is that, or the actual value of the function is, where's it at? 7.6 e minus 7, and then it's x squared plus y squared. Okay, and then on the bottom we're going to have, oh, what is it? On the bottom it's going to be 5.1 e minus 6. And then inside the parentheses, we have 3x squared plus 4900. 3x squared plus 4900. Cool. dy. Okay. Now, everywhere there's an x, because I said let's let x equal 3, it's going to become a 9. It's going to be 3 times 9 is 27. All right. So you can see that denominator is just a fraction now. And I'm just going to go ahead and bust it out to see roughly what it is. So 7.6, 7.6 e -7 divided by 5.1 e -6 times 49.27, maybe. So I get that number there, lovely. And then, so just remember, I got that number times, I actually want to do this. I'm going to grab that number times, and then in times that 9 plus y squared. This is my new function I'm going to be integrating with respect to y from 35 to 50. I just forgot my integral sign now. Too many arguments. What do you mean there's too many arguments, you goober? Did I not integrate? Integrate that times that to y from 35 to 50. Oh, she's not. Oh, because I didn't put a colon on a parenthesis. You dope. So 83%. 0.83. Okay. So a question like that could very well end up on the test. I would, if I was a betting man, I would expect that. I think would expect that, and but it would be riffing off of this sort of thing here. I will not make the K this disgusting. The K will come out decent, you know, like 5 or 0.2 or something. But it'll be like find the marginals, find the probability of this, and the other thing. I might ask you, are they independent or not? And then I'll probably ask you a probability where there is a given situation, a dependent probability or a conditional probability kind of a thing. Okay. Boop, 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 boop. Oops. Number 11 on the test is about, there's 30%, 25, and 15%. This is the kind of problem I like to screw with people on a little bit, so just fair warning. I find that humorous. And the rest. I think it's funny because people just, as soon as they see this, it's multinomial. Yeah, maybe. 25 are complaints. 15 are inquiries. This is 40/70, so the rest of the 30% are down here. And that's technical difficulties. Okay, but yes, you're probably right. Just looking at this information right off the bat, you're thinking it's multinomial. Not hypergeometric because it's not a finite number of these little things. There's a lot of them probably. Okay, so if you worked in the, I don't know, if you worked on Amazon's customer service deal, I mean, you know, 8 million calls a day amongst those zillion things. Apparently just these 4 deals here. What's probably the next 12 calls, you get this. So 12 factorial over 4 factorial, 2 factorial, 1 factorial, 5 factorial times 0.3 to the 4 times 0.25 to the 2 times 0.15 to the 1th times 0.3 to the 5th. And again, 5 and 1 is 6 plus 6 is 12. It better add up, otherwise, you know, you screwed up somewhere. I don't know what's easier. I guess this is not too bad. 12 factorial divided by 24 times 2 times 120 times 0.3 to the 4th times 0.25 to the 2th times 0.15 times 0.3 is 0.015. So 1.5% chance of this happening. Okay. Remember, you're getting kind of nitpicky about it. You're saying the next 12 calls, I want these things to happen. There are a lot of ways of outcomes, a lot of them. And so when we do that, again, none of them are going to have a very high percent chance of happening. Even if this was the most popular thing that could have happened, still not going to get a lot of them. Check it out. Out of 12 calls, 30% or 3.6 of them should have been customer service calls. I got 4, and that's pretty close. 25% of them should be complaints. Okay, well, I was expecting 3, I got 2. I'm probably not going to cry about that too hard. 15% would be 1.8 calls, I think. And then 30% would be another 3.6 of them. Okay, 7.2, 9, 12. So again, I'm a little shy on this one, or I'm a little heavy on this one. I got 5, and I was supposed to get 3.6. I'm a little shy on this guy. I was supposed to be 1.8. This one's a little over, and this one's a little over, but not terribly so. So it's one of the more likely events to have happened. It's certainly not oddball. It's a little weird, but it's not terrible. So, but again, I'm a little shocked sometimes when I see them. I still am to this day. That's a little strange. It's only 1.5% chance of that happening, but it has to do with there are that many outcomes there. 12, the platypus, normally distributed with a mean weight of 3 pounds. I wonder if I actually looked that up. I don't remember if I did or not. 3 pounds, 0.4 pounds, standard deviation. Okay. So a sample of 100 is collected. This is important. 100 is collected and weighed. What's the probability that X bar is greater than 2.86 pounds? Remember, this is the central limit theorem. So remember, X is distributed this way. X bar is distributed the same mean, but the standard deviation, divided by the square root of the sample size, which if you're playing along at home, this is 10, so that's 0.04. Okay? In other words, in our mind, we're looking at this. Okay, here's 3, 3.04, 3.08, 3.12. In other words, nobody is really bigger than 3.12. Okay, remember, this is the welcome to Freakville sign, and you can be a little freaky and live in Freakville. This is the only weirdo, only, really oddballs need to fly beyond here, okay? There's almost no chance of that. 9.2 and 2.88. Look what we're asking about. We're looking about what's probably X is greater than 2.86. Darn near 100%. But let's do the math. So our z-score is X bar, remember, minus mu over sigma over the square root of n. So for us, it's going to be 2.86 minus 3 divided by 0.04, which is 0.14 divided by 0.04, which is 3 point something. And of course, that should have been negative. You with me? Should have been negative. Negative 3.5. Okay. So in Excel, I'm going to say equals norm S dist. Remember, that's standard normal. Okay. Negative 3.5, comma 1. Right? Now, what did that just tell us? That's the probability that X is less than or equal to that value. We said it should be almost 100%, and we're right, of course. This is that it's less than 2.86. In other words, no way are you going to get an average that's less than 2.86. In fact, 99.97% of them will be greater than 2.86. Okay. Question 13 is what is that? That was the central limit theorem that allows us to do that. Okay. So if you're playing along on the review sheet there, if you roll 2 dice, there are 2 outcomes, 5 or not 5. Some of you thought there was a bunch of outcomes, that there should be the numbers 2 through 12. You're wrong. No, it's 5 or not 5. Okay. How can you get a 5 on 2 dice? We can get a 1 and a 4. Oops, I'll do it this way: a 1 and a 4, or a 4 and a 1, or 2 and a 3, or 3 and a 2. Remember, they are different. 2 and a 3, 3 and a 2 are different. If you don't believe me, and the first time I ever did this, when I was teaching, first couple of years I taught, you learn some interesting things. Some things are worthwhile, other things are kind of dumb. But I said kids are having a hard time with that. And this one buddy of mine goes, dude, you need to use colored dice. I'm like, well, what difference does it make? He's like, yes, if you have a red dice and a green dice, and the one is red, and then you do this and this, the kids get it. And it was the stupidest thing ever, but it worked. Okay, so I did that until I quit teaching probability. Okay, so I think there are 1, 2, 3, 4 outcomes that gives me a 5. 4 out of 36 total outcomes. Okay, that means there's 32 out of 36 that are not 5s. Okay, so when we do that, yeah, so I don't really like question 14. I don't really like question 14. I like the way it's phrased, per se. Well, it's okay. Let me just do this. So when you, I don't like the way it's worded. It's fine, but I don't like the way it's worded. The question should be, on average, how many times, or in other words, it should be maybe a comma at the end. In other words, how many times should you roll a 5 out of the next 100 rolls? Okay, that's probably how I should have phrased that a little better. Okay, so when I look at that first, it kind of like, what do you mean expected value? I'm looking for like 2.7 or whatever. Not so much here, because the probability of getting a 5 is what P is. Okay, and so when we look at this, we're talking about what is the expected value of getting that number of 5s, right? So how many should happen? So in other words, this is a binomial distribution, because you get a 5 or not a 5. And the expected value of a binomial is just n times p. So there's 100 of them, times 4 out of 36. Oh, I did it backwards. That'll work. There you go. So about, I should get 11.1 5s. That's what I should roll. I should roll 5s 11.1 times. So if it happened 11 times or 12 times, I probably wouldn't cry. 9 or 12 times, yeah, that's not that, or 13 times, that's not that weird. If I rolled it 2 times out of 100, that's pretty strange. If I rolled 35 5s out of 100, that's really strange. We're going to be somewhere in this ballpark. Okay. Again, that's theoretical probability. That's what should happen. Okay. 15 and 16, there'll be questions like that on the test. Examples of hypergeometrics other than we talked about in class. Examples of a binomial other than we talked about in class. Those are the sorts of things that could be on there. What I like to do is I like to ask kind of oddball questions, not unlike the discrete distributions assignment. So kind of oddball, like, for instance, the guy asking when girls out on a date in high school, probably you're going to stop when your first one says yes, probably. And so if it's a large enough school where, you've got enough possible suitors, your probability of success isn't changing that much, then it's geometric. You have to assume some things going into that. If it was like 5 girls and the first 3 already said no to you, well, yeah, your probabilities are changing wildly. So I'll tell you what, it's not geometric, because geometric probability of success must remain constant. So I'll ask questions like that on the test as well. I would expect probably somewhere between 16 and 20 questions. So yeah, they'll be pretty much, it'll look very similar to this test, with the exception of I'll make sure that my joint distributions work out, or the distributions, my K's will look a little better. And I'll make sure, like on number 3, that the thing actually integrates, properly. By the way, that would be an excellent question on number 3, where we tried to find the expected value, and the expected value was infinity or something, or the expected value wouldn't work a certain way or whatever. And I might ask you, well, how come it wouldn't work that way? I could ask you a question like, well, this one doesn't work because, or whatever it happens to be. Clearly, it's going to be a number. clearly the expected value of X is what's the most likely number to happen. And the fact that we had it where it was not coming into a number between 0 and infinity, was coming out at infinity, that's obviously an issue. It needs to be a number like 6 or 12 or 15. So I don't know. I could phrase that differently. I don't think I will. I'm not going to try to get really fancy on this test. I'm going to keep it pretty straightforward as much as I can. I will change problem number 3 on the review that I give you. I'll make it a key out. I'll change that to one again where you can just work it out and see. I'll show all my steps so you can see it properly there. And on number 5 and 6, I'll make another video explaining those two a little bit more. But as it is, as I said, it took 14 problems took me an hour to do them. So I know what will happen when I try to do the moment generating function on camera is I'll end up messing up, sit there and hem and haw for half an hour and waste everyone's time. And I don't really want to do that. So I'll make sure that it's smooth before I hand it out to you. Okay. Questions, comments, concerns, anything you want to see? I'll try to have that key up. Well, I'll have it up by Friday at the latest. I'm not going to guarantee tomorrow. Tomorrow it's pretty busy, but I'll try to get it up by Friday morning. No questions, comments? Anyone? Had a couple of questions. Yeah, well, hang out, Kelly, afterwards, if you want. Or if you want to talk now, it's cool too. Okay. All right. Well, that's all I got, people. If you want to head on out, I guess. Have a good week. If you have any questions, via email or something. All righty. Adios. Yep.
I have a question.
Yes, sir.
I talked to you earlier today during your office hours, and you said you're going to send me a email or whatnot about.
I did.
'Cause I couldn't get Excel to work. I got an email, but it didn't have any information other than our previous chats in it. I didn't see anything.
I sent you the email with the link to I gave you the average and standard deviations for those columns. That's all you wanted, isn't it? Isn't that all you wanted?
I see a link to like a Zoom meeting.
I don't know, dude. That's weird. Let me look. That's pretty weird. Alrighty then. I don't know. I sometimes wonder about myself. Yeah. Okay, sent items. Oh, you know what it is? I bet it was because I replied to your email that you sent it through Canvas, I think. Here, hang on. Here, give him a message. Oh, fart. That doesn't work, though, because it wasn't on this computer. It was on that computer. All right, I'm going to email you right now. Again, I guess.
Okay, thank you.
I think that's what happened, though. Oh, it's actually on my drive. All right, I'm not going anywhere. I just got to run in the hall and grab my drive. All right. Well, this one's going to be out. I'll use it. All right. All right. Kelly, what do you have? What's up to you? Bye. Where's this? That's weird, man. Why is that not working right? That's so weird. Search directory. Huh. I don't know. There it is. Okay. All right, there's that. Send. All right, that takes care of that. First question, still turning assignments, that's a pivot table assignments. It seems pretty late. Yeah, that's fine. Go ahead. Mhm. Oh yeah, no problem, man. No problem. Yeah, I think it's just easier than I think it's easier to make a video explaining something and try to explain it. So it's not very hard to do. Anybody else have any questions? Is there homework drop location? For the last set of homework, I put it on a 5 and 6 the other day. I haven't put a final one on yet. I'll get it done. You see your email now, Levi?
I'm reloading it right now.
Okay.
Yes, I see it.
Okie doke.
All right.
Well,
Thank you.
yep. All right. Well, have a good night then.